Our first talk is Dr. Peter Parker, who is the team lead for Advanced Measurement Systems at the NASA Langley Research Office in Virginia. He serves as an agency-wide statistical expert across NASA's aeronautics, exploration, and science mission directorates to infuse statistical thinking, engineering, and methods. If you were here last year, Dr. Parker was the recipient of the 2023 Distinguished Leadership Award at DataWorks.
Well, thanks, and I'm honored to be invited to be here. The title of my talk, you see, comes with the word practical, and that's what I expect this talk to be. I had a professor once in grad school who said this is a theory course, which means we're going to take a really simple problem and make it incredibly complicated. And in an application course, we take a really complicated problem and try to make it simple. So I'm going to try to do that. I want to acknowledge my co-author, Nathan Cruz, who I think is online, I don't know, somewhere in cyberspace. He's not physically here today, but this is definitely joint work with him. So the motivation for this presentation is that binary responses are common in aerospace and defense testing. They involve things like hit or miss. If we shoot at a target, we hit or miss. They involve things as like detect or not detect, or some kind of success or fail criteria. That's a binary response. And our objective is to have a model that allows us to predict the likelihood of that outcome, the likelihood of a hit, the likelihood of a success, as a function of one or more explanatory variables. Now, from my experience, there's often a lot more focus on the modeling of binary data, which is more sophisticated, and I'll talk about that, than there is on the design. The design meaning the levels of the X factors. And so this talk's going to try to focus, obviously, the title of the talk's on the design. Now, the other thing in practice is that design constraints, often imposed by things such as physics or ethics or resources, cost, time, always drive and restrict sample size, the range of factors, and the distribution of the factor levels. That's reality. That's not a textbook, right? That's always what we have. And I'll make that point at the end. I think every experiment has got these kinds of operational constraints and other motivations that make it less theoretical. So what I'm going to talk about is a very back-to-basics perspective on how to design experiments and to address these constraints that really it relies on the fundamentals of design of experiments. So let me start with some definitions. I've talked about a binary response. It has one of two outcomes, often coded as a 1 or a 0. Now, that's a special case of a categorical response that might have multiple levels, say 5 levels or 10 levels. In my talk, I'm not going to talk about, this is good, right? I'm going to say what I'm not going to talk about in my talk. Continuous factors that are made discrete. And that oftentimes happens, and that's just kind of a bad idea. I don't know any other way to say that. If you have continuous factors, don't make it binary. Keep it as continuous. But there are cases where there are true binary responses, and that's what I'm going to talk about. I'm also going to talk about a designed experiment, and I want to distinguish that in that we are purposefully have the ability to set the factors, the X's, to set the things that control the binary response. And I'm distinguishing that from observational data, where we collect the data, but it's not in a designed experiment. I mean, you can think of lots of cases with that where sociology or whatever are recording things where they can't really control the factors necessarily. But in our case, in most aerospace defense, we have the ability to set those factors. I'm going to talk about one factor throughout the rest of this, but it generalizes to multiple factors. And a design, when I use the word design, if you're not familiar, essentially means what are the levels of those factors and what is the order of execution. That's the simplest kind of definition of a design. Now, often for analysis, as I said, is the focus. Generalized linear models. The most common of those is logistic regression. And I've just written an equation here. This is like one of maybe two equations in my whole talk, so relax. That we can predict the probability of a 1 or a 0 as a function of the level of x. And in that equation, you see a beta 0 and a beta 1. Those would be the coefficients we want to estimate from our designed experiment. Often these fall in a general category called as a dose-response experiment. You know, when I was a grad student, I took a bioassay class. We talked about pesticides, because that's a lot more friendly than talking about people, and the level of a certain pesticide, and then the rate of its effectiveness or killing of aphids or something. I don't remember exactly what it was. But as the dose goes up, you expect to be more effective. That's a dose-response type of experiment. And dose here refers to the factor levels. It's a general case of this problem. I'm not going to focus too much on logistic regression. I've just identified it as the most common. And I'm going to try to keep this talk at the concept philosophy level, but there are many other forms of dose-response modeling. Logistic is just the most common, often because that's what's in somebody's software. But, and it's relatively simple. So let's start with a very simple case that is not aerospace and not defense. What's the probability a student passes an exam based on number of hours they study? I took this from Wikipedia. That's got all the answers, right? This is a data table for one student, and if you look across that data table, you see the top row is the number of hours they studied, and the bottom row is whether they passed or failed, where a 1 is a pass, a 0 is a fail. And if you just glance across that table, you can sort of see the trend, right? Lower hours of study relate to more likely that you will fail the exam. Higher hours of study, you see sort of that transition going from 0 to 1. And this is a very simple data table. You can see that in the data table. But I'm going to plot that, and I have plotted it on the bottom right, where you see the 1s and the 0s as dots on that plot, and you see number of hours on the x-axis. I've kind of overlaid a probability plot here with a binary plot. I find that very useful to be able to see the raw data. The raw data are the points on that plot. So on the left, I've shown this logistic regression equation again, and I show the estimates of the coefficients, and if we want to use it, we can say, what's the probability of a student passing an exam with 4 hours of study? And you plug in the numbers there, you can do it in your hand calculator, and you come up with about 86%. And I just showed that on the plot. Now there's several points I want to make on this plot before we all get wrapped up about examples that we like aerospace and defense. And so one is, if you look at this plot, and to your left, you're looking across, you see a region where there are all zeros, and to the far right, you see a region where there are all ones. You see these distinct regions of zeros and ones, and in the middle, you see a mixture. You can sort of see that in the data table too, right? You see overlap in the mixture. This is sort of ideal. This is a textbook example. This is what I have never seen in practice, nor will you probably see in practice. But notionally, you want this area where you have consistency on both ends, the overlap, and the amount of overlap determines the slope of that line. It's the uncertainty, right? I mean, that's what makes this not a step function. If this was deterministic, you'd go zeros, step straight up to ones, and go ones. But it's not. There's variability in this result. The other thing I want to point out is throughout this talk, I'm not going to show confidence intervals around that line, but they are there. And in fact, the confidence intervals on this small data set would be pretty wide. And in most cases, the applications I have, we care about one side of that confidence interval, an upper or lower bound. But for simplicity, I'm just going to show that's the mean line to show the shape of the curve. All right, so I'm going to illustrate two case studies, one just briefly and one with a little more detail. This one involves nondestructive evaluation, and there was a really nice session, I see Elizabeth in the back, earlier today that talked about probability of detection, nondestructive evaluation techniques. These are techniques often used in medical practice as well, ultrasound, x-ray, but we use it on metal parts. or any kind of part, looking for cracks, flaws, anomalies, inclusions. And for each of those techniques, we want to know what their probability of detection is, which means what's the flaw size, or the largest flaw size we might miss is really practically what it turns into, but the flaw size that gives us a certain level of probability detection with a certain confidence level. Confidence level reflects the uncertainty in the data set that we have. The application for this, and where I spend about maybe a third of my time, is in fracture critical human spaceflight articles. They are required to demonstrate, each technique is required to demonstrate this probability of detection, and to do that, we conduct an experiment. If you went to the session earlier today, there was a lot of talk about simulation. I'm only going to talk about physical experiments, which is for human spaceflight applications required that inspectors either have pre-certified or demonstrate this capability. And so how would you do that? Well, you take samples that have flaws of different sizes, you present it to the inspectors, and they report back, it's blind to them, they report back whether they found it, that's a hit, or whether they missed it. So as you would expect, flaw sizes get smaller, you get more misses, flaw sizes get larger, you get more hits. The plot I've shown there is some real data, and I've talked about this 90% probability of detection. So what do you see in this plot that's different than the textbook simple study example? You see no overlap on the far left of where you're consistently missing. Well, let's think about this for a minute. If I'm making these specimens, they are very expensive. These probability of detection studies could be in the hundreds of thousands to millions of dollars. Spaceflight components with induced cracks, grown to specific sizes. And I don't want to make a whole lot of them that he never finds, right? I'm not interested in making a whole lot of small cracks that the inspector never finds. That's not practically, important to me. I'm also not interested in making so many that they're so large that he can just look at them. He doesn't even need to use an instrument and see the crack. So I'm really interested in this one focused area, and that distribution of points that you see there sort of reflects that. I want to predict that 90% probability of detection point. I put another line on there, 10%, and that's sort of a question. Would I predict the 10% probability of detection from the data that are on that plot? I shouldn't, because I really don't have the information there, right? I'd be extrapolating. And so this idea of what data you have, where you want to focus is very common. We want to focus our efforts in defining this portion of the curve, not the entire curve. And that is where we start to differ from typical dose-response relationships like I had in grad school. So my second example has to do with measuring human probability of annoyance, human annoyance. And if you've been in DataWorks sessions last year, we had a keynote on one of those programs, the development of the Quests program and the X-59 aircraft, which is a picture of it there. The idea is to fly over communities in the United States and measure human annoyance to a tailored, attenuated sonic boom. Right now, that is something to be proven in an experiment. There's been a lot of prior work, and I'm going to show some results from that. But the way the experiment is conducted is we fly this experimental aircraft at varying dose levels, which is a little more complicated than loudness. And a colleague of mine in the back is really the acoustician who's going to take all the hard questions if somebody asks me what that is. But imagine it's loudness for now. And it flies at different altitudes, different configurations to vary that dose. And then we measure whether people are highly annoyed or not. That enables us then to inform regulators and aircraft designers as to what is an acceptable noise level of an aircraft that flew supersonic speeds but did not deliver a traditional sonic boom, which is currently banned by the FAA for commercial aircraft over populated areas. So we might be interested in predicting now a very low tail. 5% of the American public maybe that is highly annoyed. What is the dose that would do that with an associated confidence level? So now the first example I showed you, I was up on the high end of that distribution. Now I'm focused on the low end, and kind of keep that in mind when we talk about potential designs. So there were two studies that have been flown. There's more than that, but two that we look at. One is called Whisper. It was flown in 2011. Waveform and sonic. It's an acronym. Something response, perceived response. And that top plot are the ones and zeros for highly annoyed from about 2,000 survey respondents. Now, what's the first thing you see in the upper plot? You don't see clear separation of ones and zeros. Well, that's by design. We don't want to fly it at such a level in which 100% of the people are annoyed. That's not good for NASA's brand, by the way. To conduct an experiment, we annoy everybody. But that's far outside the range of what our interest is as well. We want to know this low end. Now, is there even, a region, there is a region to the left, which you see, no annoyed, zeros, but it's the line that's on there really depicts the challenge. We're just barely in the tail of this distribution of picking up human annoyance. And so how would you design that test? If you chose the levels, how would you design it? The bottom one is another test that was flown in 2018. QSF, Quiet Supersonic Flight, I think, is the acronym. And this one you'll notice was flown over a narrower range, only up to about 90. This is perceived noise level, dB. The dashed line shows an extrapolation beyond that, and there's about 5,000 subjects plotted on there. You see similar things. You even see a little less separation on the far left, but you're in this very low tail. And if you focus on that bottom plot before where the dashed line is, can you see the line curving up? Well, I've got this plotted up to 100%, and I will tell you if you expand the scale, you'll start to see it. But you're really just picking up on the onset of annoyance. And one question that might come from this is, should we be using a logistic model in this very narrow range? Most of it's extrapolating, right? The rest of the logistic model. And I think that's part of one of the messages I'm going to say today is to think about challenging what, and in one of my slides I say the desirements are versus what you can do to manage the expectations. Now we might be interested in predicting annoyance at about 85 dB in this example. So there's some real data. I'm going to talk a little bit about planning of the next experiment. And it's really just motivation. These are not hard numbers that this is the design or the plan, but I want to sort of motivate some of those constraints with real numbers and be less abstract. So each noise level, to get one response from a collection of survey respondents, requires a flight of experimental aircraft. Expensive. We have a limited number of flights that are going to be done per day. It's something about 3 to 4 operational tempo, and a limited number at each community site around the United States. And that turns out to be about 80 flights over 5 weeks. That's a small sample size. For binary responses, any textbook would probably tell you shouldn't do that. Also, we're restricted on too high of a noise level. I sort of alluded to that. That can have ethical concerns, can be painful, can be traumatic. And so the response is constrained to about 15% highly annoyed. The range of noise levels is constrained by how quiet the aircraft can fly. And so it's a relatively narrow range to detect this onset of annoyance. And the last point is that the ability to set the design point to control the X factor is challenged by the aircraft environment, the atmospheric conditions of the day, but also the performance modeling of the aircraft. We are measuring those noise levels, but they are measured with error. It's not the assumption that the X's are known without error. That's always usually baked into simple, any type of regression. That's usually the basic assumption, but particularly in this case with logistic regression. That's a subject of a whole nother talk about measurement variables, measurement error, that my colleague Nathan Cruz will be giving at joint statistical meetings later this year. But I'm not going to talk about it other than just raise it to your attention. So there are a lot of limitations in available guidance for design of experiments with binary responses. So I guess I would like to see a show of hands. How many people have been in a design of experiments course and they gave guidance specific to how to set the X levels for binary responses? Maybe the first question is, did you talk about binary responses? But okay, we got a few. That's great. And was that guidance based on specific to a binary response, or was it just an adaptation of traditional design of experiments? I'll leave that as an open question. It's usually just kind of an adaptation. And then did it assume that you'd have larger sample sizes? I'm guessing you probably did. And that they were nicely spread across the dose-response relationship, not just in a tail of the distribution. And did you talk about operational constraints on being able to set those, or what is possible and what is desired based on resources? So you put all that together, you have a real-world problem, right? But the elements of building a design, I'm going to argue, are basically the same philosophically as all of design of experiments. Collaboration with subject matter experts. It's essential in all cases. It is, especially in binary responses, to understand, the operational constraints, the existing literature, the presuppositions about how we think responses will happen, and then to get it in their terminology, colloquial terminology that they would use. And explaining the statistical design concepts in that language is very helpful in realizing some of the things I've pointed out already about limitations of what is possible and what can be done under the constraints that are there. Basic philosophy of design of experiments. How many design points? Which ones? And in what order? There's design of experiments in a sentence. That's what it's about. Replication, randomization, and blocking all still apply for different reasons, but they all still are part of that. And blocking, in particular, may be a very effective strategy for operational mitigation of potential disruptions in the test. Now, I don't know anybody here that conducts real tests. You ever had it disrupted? Yeah. Okay, I thought so. Have you ever had one that wasn't disrupted, that past day one, that went as you expected? And I already mentioned about challenging sort of the desirements and the requirements, especially for binary responses. Because of this assumption, I think, about the ability to model that logistic curve, and you've heard me sort of hint at it, just because you can, should you? Just because you can do that, should you? So I want to talk about a couple of candidate designs just to kind of help us to practice some of the ideas that I've said. So the upper one is a baseline design, and none of these are the actual designs. These are just for illustration. So for the noise annoyance experiment, if I flew the baseline design up there at the top, you see that I have a large distribution of flights to the low end, I have some to the high end, and I have not many in the middle. The ones on the left side where I'm not going to solicit a response are maybe not the best investment in my 80 flights. I'm not going to learn about the onset of annoyance if I fly a whole lot of flights at a low level. And so if you quickly glance down to the next one, you see it's distributed differently. More of a push toward the high level. More of a push toward trying to get that rare response to be solicited of high annoyance. Also, you notice on the upper one, there's many discrete levels. I told you that set point control was very difficult. Does that make sense, to have a lot of discrete levels when you can't really control the levels very well? We're still going to measure them, and we talked about that with error, but the bottom one you see are 4 discrete levels. Well, how many levels do I need? Well, this gets back to sort of classical design of experiments. How many coefficients do I have to estimate? And maybe 4 is enough. Maybe you want more, but with set point control, it starts to become kind of that you're feeling like you have more control than you do when you can't really set those levels. So there's just a comparison of how to think through the process. Where do I invest my doses? How do I distribute those doses? This is very practical. This is not optimal design. I did not tell you any optimization criteria, just practical applications. In terms of blocking, consider that last design I showed you on the previous slide with the 4 discrete levels. How would you allocate that across 5 weeks of testing? Well, I'm going to show you two thought process approaches to that. The top one I'll call optimistic. You could also call it maybe unrealistic, where we expect a complete test campaign to be done without disruption. And in that case, you might want to distribute the levels equally across the 5 weeks. And I've shown just notionally how that might be done in the top block up there. Now, a more pragmatic approach, or as my co-author said, I'm just playing with words about being pessimistic, robustness to campaign disruptions, I would want to maximize the information early with an experimental aircraft or developmental test. And I don't know if the test is going to end prematurely because of maintenance issues or whatever. And so you'll notice the 5 weeks there, and I sort of stack the same philosophy, high-end, high-dose responses in week 1, and then I kind of bookend them toward the end. This is just a thought process, right? This is not, once again, an optimization criteria, but how you might want to do that. Bookending them gives me something about maybe being able to measure how much the participants acclimate to the noise from week 1 to week 5. And I really want to solicit those rare responses. Okay, so some concluding remarks. I'll claim that experiments with binary responses are common, and they always involve practical constraints. It's a little bit like the phrase that every experiment has randomization restrictions. That's not an unusual thing, that's practical. The experimental design guidance, I think, is very limited in binary experiments. And I'd welcome a comment on that if you disagree, but I think there's often this overly focus on the modeling. Maybe somebody says, well, let's just uniformly distribute it. And that might work if you're going to do the full dose response curve. But when you're in a narrow region, I don't think just uniformly distributing it makes sense. I think the experimental designs are often underappreciated. A focus on the design or overlooked, and that's due to this overemphasis on modeling. And collaboration is always essential. But hopefully what I've explained to you is that the foundational concepts of DOE still apply, even in binary experiments. That's a concept and a philosophy of design of experiments. It's not a particular application of a particular method or tool. It's this concept about how do we make every data point work as hard as we can and get as much information as possible in order to build the models and the utility that we want to get. And with that, I will conclude.
Hello, Peter. I've seen you around before. I'm sure you were here last year. One of my former summer associates is actually going to be working at IDA in the future. Actually, I'll wait. Sorry. No worries. Hello, Peter. So this is Curtis Miller at IDA. And so as I was saying, last year I had a former summer associate of mine who will kind of start working at IDA. His name was Addison Adams, where we kind of looked into trying to come up with guidance for using binary experiments and or using DOE for binary experiments. In fact, I've been thinking about this for some time. One thing that we were looking at was optimal DOE for binary experiments. And long story short, we were surprised to find that the optimal designs, even though they satisfy the supposed optimality criteria, were not getting better power than the designs that were made for normal responses, which was often designs that were just like full factorial. So, yeah, so far, like, regarding that second point, we haven't been able to come up with anything because we haven't been able to come up with anything better than what we have now, right? So, I guess in light of that, what other kind of guidance do you think would be useful to you for binary experiments?
So I think, your assumption about, well, I think you've sort of solidified my point. There isn't good guidance out there as you're searching for it. But I think that when you think about binary experiments, it's really what do you want to say? So I'll just, for this flight, do we really want a full dose response curve, or do we really just want to be able to say that below a certain dose, there's this probability of annoyance, recasting the problem in much more simple. And if you did that, more like a hypothesis test, how would you design that? That's a different philosophy than a continuous model. And so I guess I'm not looking for optimal type approaches or something like that. More, I'm encouraging people to look at the practical utility of a binary response experiment and maybe recast the problem in a different way. As I showed you with these tail probabilities, you can model those as a dose response, but I don't know that you should.